Oh, hey, hi, good morning, afternoon, good evening. Um, Session five, let's talk about some of the ways that we are interacting with our hardware. So, what are we going to do today? Well, we're going to actually end up doing some wireframe drawing. Turns out we're not the first people to do it. For about 500 years, artists have been drawing wireframe just so give a sense of the whole object. So here's a perspective study of a chalice from Paolo Uccello, 1450. We can do them a little bit faster now. Probably took them a few days to do that. We have mentioned a couple of people who were critical to the development of computer graphics. Van Dam, Andrew Van Dam is one of these. He's been teaching since 1964-5 at Brown, and he's a little bit older than I am. I was born in 63. Assignment 3 and 4 will be released by the time we're in the lecture. Do a Git pull. Get started early. Um, do assignment 3 first, and then take your knowledge from that and take it over to assignment 4. Um, in the first one, you're going to be parsing positions, then colors, then textures. Yeah, just positions and textures. And then in the next one, you'll be doing normals. Last class, we talked about transformations. We ended up the class with scale, rotation, and translation. Um, we played a little bit with OpenSCAD, and we saw that the order in which we apply these transformations is important. And in particular, you did an exercise where you developed code for scaling around a point. And who knew there was such a thing as scaling around a point? Rotating around a point makes sense because you have an axle and things spin around it, but scaling around a point means that everything, if you scale around this point, everything kind of grows away from this point. So you did that. It was great. OpenSCAD is a great way for you to experiment with some of these things if you just remember that those translate commands in there are just matrix multiplications. We also saw vectors. We saw how to do a dot product and get the cosine of the angle between two vectors and the cross product to generate an angle that is perpendicular to both of the vectors. Today we're going to talk about WebGL and GLSL. It's actually kind of a recap of what you did for the last assignment. It's doing it and then learning how it works. We're going to add some color. We already did that, understand our shader. We'll talk, but most of what we're going to try and get into is how the CPU and the GPU talk to each other, and then we'll see some model space transformations. And in class, we'll do a brief little exercise where we do a rotation. Hopefully, we can do that rotation in our little frame buffer because I've implemented vertex shaders and fragment shaders in our frame buffer. So we'll do that there. So, programming in WebGL and GLSL. We're going to talk about GLSL today. It's overwhelming where we are. You know, you guys you're troopers. You're learning TypeScript. You're being forced to work in React, and you're in this web browser. The reason that I picked TypeScript is so that everyone has a kind of a uniform environment. We found out on this assignment that reading files from Windows, you actually have to deal with a carriage return as well as a new line. But for the most part, our platform is consistent across all of them. Our stack is React, TypeScript, and WebGL2. We are going to, we talked about transformations last class, but we talked about them from a mathematical perspective. And we're going to kind of come back to graphics and start to think about how do we use these transformations in our graphics pipeline, and how do we tell the hardware, how does the hardware do it? It's all going to come together over this lecture, the next lecture, and these assignments. We're using GL Matrix. So one of the things that we used to do in the old days when we taught computer graphics, of course, we'd say, write yourself a matrix library. But it turns out that's not really that useful of an exercise. It's more useful if you're doing a numerical analysis course, because then you can deal with round off errors, stuff like that. But for this particular course, we're going to use GL. GeoMatrix is used by over 100,000 projects. It is very simple. It kind of looks like what you did in OpenSCAD. It's very straightforward. You just build out your stack of matrices, you multiply them together, and then we're going to figure out how to send that to the hardware. So let's go back and talk about GLSL, the OpenGL shading language. The blue cubes, the blue squares that we see here are the ones where we can write programs for. In this course, we're only focused on two, and we're going to be using the language of choice, which is GLSL for OpenGL. It looks C-based. There's no surprises here. It's a very simple language. We're going to talk about kind of some of the constructs of that language, some of the types. They're very simple. And we'll talk about debugging at the end a little bit. So these are the two programs that we're going to use. You will recall that we wrote a program that had two shaders attached to it. You can store those programs in your memory, and then you can render different objects. So you could have like the shiny sphere, and then you could have a matte car driving by, and both of those would use different shaders. You don't have to recompile them every time. You just do that as you load. When you load your level, you compile all your shaders, and they're ready to go. Then you can just start rendering. GLSL is a very simple language. Fortunately, you can use this if you could have comments. Same thing as in C or Java, or TypeScript. You have kind of scalar variables, int, float, and bool. You can cast between them. It means you can convert between them. In TypeScript, you use ceiling and floor, etc., etc. You have for loops and conditional statements, pretty much the same as C programming. You can't have recursion. That's because of the hardware limitations. You can have structs around, so you can pass things around as a struct. Matrices are, there's built-in types that have a whole bunch of functionality to them. We'll see that in a second. Vector 2, 3, 4, iVector 2, 3, 4, Boolean vector 2, 3, 4, matrix 2, 3, 4. They're always floats. The way that a matrix is stored is in column major order. So if you have that matrix on the upper right-hand corner of your screen, you can see how it's laid out in memory. There's a whole bunch of built-in variables that you can use within your shaders. So you get the vertex ID, etc. So we won't necessarily be touching on all of these. And then your fragment language has a whole bunch of different information that allows you to make decisions as to whether things are visible or not, what color they are, etc., etc. Accessing the data. This is kind of fun because you have a vector 4, which has array accessors and Swizzler accessors. So my vec(x), there's a convention that x, y, z, w. That's the 4 for vector 4. Now notice that fourth row right here, where you do this. I've added an x and a z, and that does kind of what you don't expect. Well, you expect it once you see it, but you want this value and this value. So it's going to return 0.9 and 0, 0, and RB, because RGB also maps to a 3D RGB alpha matches to a four-dimensional vector, so that you can get R here, GB gets that one there. They basically, this says that you're working with color, and you can swizzle, so you can swizzle them around. Interesting stuff. I find it kind of confusing to be doing this. It's really easy to, you don't know if this is a typo or if it was actually intended. I prefer this notation here myself. Okay, so what is OpenGL? OpenGL is a state machine. It is a bunch of people that are sitting there ready to make triangles appear on the screen. And you have to give them data such that they can all grab a triangle from this data, draw it out, and then send it back out so it's displayed on the screen. That's exactly what OpenGL is. But in order to get these group of people to each one of them do one or more triangles, you actually have to give them the data. And that's what a lot of that code that you saw in Canvas GL, it's doing all of that. You know, if you recall, we do the vertex buffers and very tedious, and then we do the array buffers, and then we do the index buffers, and then we tie it all together, and then we say, okay, go. And it's actually going to get more complicated now because we're going to add transformations and rotations, and we'll see how to do that. But it all makes sense. We have, it's a state machine, so before you do render, before you say draw the triangles, you're basically setting a whole bunch of parameters within this machine, and off it goes. Now, you can see in this particular OpenGL context, which is from Mesa, which is an open source GL, you'll also see in the frame buffer code that we use today how we have a context that we set up. I've kind of made, it's a simpler version of this. Mesa tries to be like a complete GL implementation. Mine is just a little baby one so that we can play with it and understand it. It's a state machine. That means that from one state you can go to another one. And so here's the state machine for OpenGL 4.6. It gets quite complicated, but in our situation, we're just going to think of this as we specify the vertices, we run the vertex shader, a whole bunch of stuff happens in the machine here, and then we have the fragment shader, and it does its thing, and then we do per sample operations, and off you go. There you go. Boom. So you've written your shader, it doesn't work. What the heck? What's going on here? You know, this is basically what happened here. I have this thing here. This is my monkey. You're going to see the monkey will appear on your screen during this class. And the code that I was using to render this is here. Basically, if render mode is wireframe, basically go through and draw each of the lines. There's a big hint for your next assignment. Oh, this might actually just give away most of the code. But anyways, there you go. And then you draw, in here I draw elements with my triangles after I've set it all up, right? But you already saw that. So what do you do? Well, GL get error is something, remember, you're interacting with a state machine. So you do something. Now you could have set that up properly, or you could have messed it up. So what you do when you're setting up your pipeline, you use GL error quite a lot, and so that you know that things are going well. See, so see OpenGL ES3, it's right there. And the types of errors you can get are no error, that means you did the right thing. Invalid enum, that means that you've used an enumerator of some sort. Invalid value, there's a whole bunch of things. You can look these all up. But what I don't like about this one is that for every good thing, you're going to get a lot of information. So I'd rather use this one here where I don't have anything printed out here. So we're just going to do nothing for no error. And so here we have this thing here that results in my monkeys looking like this. So for solid, I have this, and for wireframe, I have this. So let's go back, look at the code here. What's different? Well, this here looks different than that. Well, yep, that's actually the bug. GL is expecting an unsigned short, not a signed short. Now, the difference between those two is that how the numbers that it represents. So with an unsigned short, you go from 0 to the max size, and from signed short, it actually interprets it from minus half the max size to plus half the max size that can be represented by that. So these are indices into a triangle, so a negative makes no sense. So they've actually hard-coded this. Now, this is a very interesting and important point, is that you're interacting with a very highly tuned piece of machinery that expects things. It's not very in fact, it's not forgiving at all. You know, you think, oh, what's the difference? A short is a short is a short. 16 bits is 16 bits. Yeah, no, not really, because an unsigned short is interpreted in a completely different way than a short. So um, this is important. So when we fix this, so when I run that, I get this thing invalid enum here. That's the error that I get, and that's the fix. I change that to unsigned short, and I get the monkey. And here, let's go have a look at the monkey here. Let's see, the monkey is, no, the monkey's not there. The monkey is here. Let's go have a look at the monkey. Monkey, there's my monkey, there's my wireframe monkey, and there's my monkey. Okay, let's go back here. So, debugging GL has been difficult, and the OpenGL consortium have recognized this, so they've actually added more powerful debugging in OpenGL 4. We're not going to cover it here. What we're doing here is simple enough that we don't need to worry about it. So we have some tools that allow us to debug, and so now we know that we can go in for every time we interact with the state machine, we can say, did I do okay? It's like, okay, do something. Am I okay? Do something. Am I okay? That's basically what you want to do. So let's go through the pipeline. Vertex specification. We talk about vertices. It's a point. It's an XY or XYZ, or Z if you're in Canada, Z if you're in the States. And you look at our 3D pipeline. We have to specify the vertex position data, right? It's actually the only thing that you absolutely have to do. So we did in the last assignment, you saw how we can add color to vertices. We're going to step away from that, and we're going to come back to doing color through textures, because in general we don't paint the vertices. In general, we use textures. It's just an easier way to do that. So this will be the last time you see color attributes as part of your data, but we did see how you could do that. But it is useful for us remembering how we interleave data. So we built a triangle with colors. We had a fragment shader, and we said the color is equal to the color. So basically, the interpolator interpolated the color, and we wrote code for that. Remember in our class exercise where we interpolate this color and this color, get this color, and we interpolate this color and this color and get this color, and then we interpolate across there and we get this beautiful kind of shade. It's a fairly straightforward approach, but we get this, and we've played with this when you did your sliders. I hope you all kind of there wiggle the sliders back and forth, because you can see how it blends there. So what did we do? What we did was we interleaved our vertex attributes. You added the indices to the data so that it would render properly, and then then we added indices. You could see how we had this vertex buffer object with the indices approach attached to it. So if you go back into the code, you'll see this call to vertex attribute pointer. What it's doing is it's telling the GPU how to put data into the vertex shader. So in this particular case, you have this big array of floating point values. You have XYZ and then something, and then you have RGB and then something, and XYZ and something. And the vertex shader needs to know, how do I get the data from this mysterious memory location that exists? How does that get into the shader such that I can run my code and I can spit out a new value for that? Well, that's what this vertex attribute pointer is for. So we enable this attribute array, and then we say, okay, this is how we're going to access it. And if you recall, we stored our data as XYZ RGB, and then we specified where the vertices are and where the colors are, and then we were able to render that beautiful little hexagon and those rectangles such that they would do this. then tell our shader where the data is. This location here says how many of these over do you have to go. So location 0 means you start at the very, like right there, and location 1 means step 1 vector 3 over. So in this particular case, we have a 3 vector for XYZ and we have a 3 vector for RGB. And that all makes sense. In the code, that's what we do in the code. And so how does OpenGL interpolate color? Well, it's exactly what we did in our class. We won't skip over this. It's linear interpolation. It looks nice. It's not perspective. It's not perceptually correct, but that's what we have. We have OpenGL rotation. This is not necessary for assignment 3. If you want to throw it in there, it won't bother me at all. But I might as well wait for assignment 4 because then you get nice textured things spinning around. We played with OpenSCAD and we saw how we can transform objects in the world such that they move around, and we have a rotation, translation, and scale matrix, and we saw how we could put those together. And so let's go through and do the next slide. If I use the GL matrix rotation, you'll notice that I have these rotate X, Y, and Z, X, Y, and Z in this order, that you can apply to your rotation. And this is basically what you do in code. You say generate a model matrix, which is of type mat4, and then I create an identity. Then I will rotate that matrix and store the matrix here. The rotate, this graphics library, this is the source matrix and this is the target matrix, and this is the matrix that you're multiplying it by. So this says generate a rotation matrix around Y with this angle, multiply it by this, and put the result in there. Now, we've set up our matrix. How do we get it into the GPU? This is the part we've been waiting for. We could do a couple of things. We could make a new matrix buffer and we could do the transformations ourselves. Yeah, no, that's not very good. We could update the created data with new vertex position. Yeah, no, that's not very good because there's a whole bunch of, yeah. Let's just figure out how to get the GPU to do it. So what we need to do is figure out how to tell what the GPU, what the matrix is that we want it to use, and then Bob's your uncle, off you go. It will let it happen. So what we're going to use is this concept of GL uniforms. We already talked about data buffers, where we set up a buffer and they're like large pieces of like many thousands of vertices that you can put in there. But there's these other smaller pieces of information like a matrix or a scale that you can add to your code to make it do things. And so rather than having another buffer for that, they have actually fixed size containers for these. These are the GL uniforms. They can be of different types. So it's a global variable that's available to all of the shaders. It is exactly like a global variable. I know we're all told not to use global variables, and here am I telling you to use global variables. That's okay. Get used to it. We're now at the very, very core of hardware where global variables actually make sense. So our shaders will look like this. I have some value and I can add it to Z. Notice that I can also add it in my fragment shader, and then that will give me these values here. So we have to tell the GPU that we're going to use a uniform, and then we also need to get that uniform into our GPU. So they're like vertex buffers. They kind of, but they're passing a different type of data across. So basically, what you do is you get the uniform location and you set it. So in our shader, we say, I'm using this uniform here. So in the code that I've written for assignment 4, I have this thing here. I get const rotation matrix location. I basically say get uniform location or shader program matrix model matrix. That's in my source code. Then I set the rotation to be that. Simple, quite simple, straightforward. It's just tedious. And then in the rotation, this is the version 410 core, but we'll have a look at it in ours. We already did. It's in the code. Yep. And then my uniform is here, my model matrix, and then I can just use it here. So basically, I will set my model matrix to there. This is the C version. Drop the U, and you have what we're using. So we now know that we can take our matrix, we can add it, we can use it in a vertex shader. We'll play with that in class. We've also talked in a previous assignment about meshes. We actually built a mesh. You built a mesh that represented a hexagon, and you built a mesh that represented a rectangle with 6 triangles. And you saw that you could actually reduce the amount of data that you send to the GPU if you use the index vertex buffer object. So this particular model, which is in your resources file, you can see it there. It's a lot of triangles. There's also a 2% version, which is 2% of all of these triangles. It loads a lot faster. We did look at a single vertex buffer that we would send over and say, here's your data. Every blunk is a triangle, off you go. And then we also looked at elements in the index buffer, and we're deciding to follow that path on this course. In particular, for assignments 3, 4, and 5, that's exactly what we're going to be doing. So this is the way we're not going to do it, where we just put everything into a single buffer object, and we say every 3 of these is a vertex, and then we have to duplicate data. It's not what we want to do. We're going to do this. We're going to have an index set, index face set, and off you go. There's edge-based data structures that are useful for representing triangles, but we're not going to follow that. That comes into play with constructed solid geometry and a whole bunch of other stuff. For now, we don't have to worry about that. Assignment 3, assignment 4, object model format, assignment 5. We're going to read the positions from the file. We're going to read the textures and the texture coordinates. So your PPM file loader comes back, and we're going to use that in assignment 4. In assignment 5, we will be doing lighting, and we will have normals. We can import those from our models as well. So the object model format looks like this. It's an old one, but it's a good one. You have vertices, they're X, Y, Z, and W. W, if it's not there, you can assume for this course, you don't even actually have, you don't have to worry about W. You can just have vertices as 3, because as we saw, the shader can add that 4th dimension. Texture coordinates, normal coordinates, parameter spaces for UV. We're not going to deal with this one. And then you have these faces. You can have a face that is vertex 1, vertex 2, vertex 3. You can have a face that is vertex 1, texture 1. That means it's the first element of the texture, so it would be this one. You can have this one, which is vertex texture normal, or you can have this one, which is vertex nothing normal. And then line elements, don't worry about that. We're not going to use VP or L, as I said. We are going to be writing code that we will load these files up. I've provided, hopefully, a nice framework in which you can just focus on reading the file and parsing it and stuff like that. And then you'll be able to see some models on your screen. It's kind of cool. So assignment 3, what you are going to be doing is making this happen in your triangle. You're going to start off with a triangle, and you're going to make it a wireframe. You're going to do that. And then you're going to get courageous, and you're going to make sure that this one works. These are both defined in files. Then you're going to go here, and you're going to go, ooh, there's a bunny. Ooh, that took a long time to load. But there's my bunny. And then I'm going to do a monkey, and I'm going to do a teapot. And once you've got these 5 objects rendering like this on the screen, then you'll be ready for assignment 4, which is where we add textures and normals. So you can use assignment 3 as kind of a throwaway. Assignment 4 gets a little bit more complicated, but assignment 4 should set you up for assignment 5, so you have normals loaded into your models. Okay? And where are we? This is what your object model TypeScript representation looks like. I'm finalizing this right now. By the time you get to the lecture, this will be there with like a default object, such that if you click on a button but you haven't read it from the file, it will just produce like a little silly object or something like that. So that's there, and I'll also walk through the code and what needs to be done. There are other model objects, other model formats that allow you to deal with articulated objects, skinned objects, etc., etc. This all gets incredibly fun and incredibly complicated as you go out from there. But for the purpose of this course, we're just going to do this one. So what we are going to do at the very end in the class, once we get through answering all the questions about GL attribute and how it all works together, we are going to go through and we're going to do 2 things. We're going to add a rotation. Just I'll show you how to do that. But hopefully, we're going to do draw elements from our frame buffer, and I'll show you the shaders that exist in that now, such that we can do a little rotation in our little silly frame buffer. That'd be cool. And there's no more extras on this one, so thanks for watching. I will see you on Thursday. Bye.